Let's talk about rotational energy. By now, especially after covering energy, you should understand that energy is a very important concept. And an object that's rotating is going to have energy, and we would like to be able to know how much energy that object's going to have. So that's what this video is really about. It's introducing how we find the rotational energy for an object that's rotating. And then we're going to look at the concept of the moment of inertia, which flows out of this, okay? So let's talk about rotational energy here for just a bit. The key to determining the rotational energy of a rigid body is just considering the energy of every piece that makes up that rigid body. If we can start down at that smaller level, then we can work our way up to a larger level. So let me put up a figure here and illustrate some of this. Suppose we have an object. Now, right now, I'm kind of treating this as a flat object, but this applies to objects that are three-dimensional as well. It's just two-dimensional is easier to draw. But what we're going to do is have this object. It's irregularly shaped. I did that on purpose because I don't want you to think that what we're finding right now requires a beautiful shape in the object, okay? And what I'm going to do is I'm going to put in a point that represents the axis of rotation. Now, the axis of rotation is just a line that you can imagine that's going through the object, and the object is rotating around that line at the point at which it's going through the object. So we're seeing the axis of rotation in this picture from the top, and it's perpendicular then to this shape right here, and everything's going to spin around it. And it's going to rotate. We're going to give it an angular velocity that we're going to call omega, okay? Which makes sense. That's what we use for angular velocity. Now, I said what we want to do is we want to look at each little piece of this and consider the energy of each little piece first. So let's do that. Let me just put in a few pieces that make up this object. So this is a little, you can think of it as a small particle that is part of this overall object, and the same for these. And I've got three of them drawn out here, and they all are a different distance, okay, from that axis of rotation. Now, if they're all rotating around this axis, remember, that means that all of them are going in a circular path around that axis. That's what they'll have to do. But each of them is going to have a linear velocity, right? So let me draw in the velocity vectors. I don't know if you remember, but the velocity vector for an object that was moving in a circle is always perpendicular to its position vector. And so if I were to draw the velocity vectors in, they're going to look something like this. I've got velocity v1, v2, and v3. And if you notice, I've drawn the arrows a little bit longer for each one. I did that intentionally because as we go from particle 1, 2, to 3, they're all getting a little bit further from that axis of rotation. And so they're going in bigger circles, and that means that they have to move faster. So the objects that are further away are moving a little bit quicker. Now, let's think about this. Each little piece that I've emphasized here, well, it's got kinetic energy because it's moving, right? And you know that the kinetic energy of anything is just given by 1/2 times its mass times its velocity squared. And so each of these, I could calculate the kinetic energy of each little piece just by doing this equation. But I want to write this a little differently because remember, we're going in a circle, and the velocity of something that's moving in a circle connects with the angular velocity that it's moving at. Remember, that's why I emphasized this earlier. And so we can say that the individual velocity of each little particle is actually equal to r omega. That's something we talked about back there when we were talking about angular velocity. If I know my angular velocity, I can get my linear velocity, or the magnitude of it, just by multiplying that angular speed, that angular rate, by its distance from its axis of rotation. And so v here, well, that's actually equal to r sub I times w. Now notice I didn't put an I on the w because remember, now I emphasize this a lot when I was going over that stuff, everything that makes up this object has to have the same angular velocity. They all share that in common. They don't have the same linear speeds, but they do all have the same angular speed of sorts, angular velocity. So what this means then is I can write the kinetic energy of each of any of these particles as 1/2 m sub I times r sub I squared times omega squared. And what I've done here is I've substituted the r sub I omega in for v. And of course I got that square term, which is why the square is showing up on both the r and the omega. So this is an expression for the kinetic energy of each of these little pieces of the object, given in terms of how far they are from the axis of rotation and the angular velocity at which they're moving. So that's one little piece. Now here's the thing. Say I wanted to find the total rotational energy. Well, then the way I could do that is I could just add up the kinetic energies of each of the little pieces. Just add up the kinetic energy of this piece and this piece and this piece and all the other pieces that make up this object, and that's going to give me my rotational energy. So rotational energy, it's due to rotation, but I want you to see it's really just kinetic energy. We're just adding up the kinetic energy of every little piece that makes up the object. And so I can take this over. Let me use my expression I have here, and what I get then is that the total energy, the rotational energy, is just equal to 1/2 m sub I r sub I squared omega squared, adding those up over every particle, however many particles there are that make up this object, however I choose to divide it. This would give me the kinetic energy. Now, just pulling a little bit out of your math background, remember, just like with integrals, with sums, if we have values that are in the sum that are constant, that don't change, then we can pull those constants out of the summation. And in this case, the 1/2 is obviously a constant. And omega, we're assuming the object is moving right now at a constant angular velocity. So omega isn't going to change either. Okay? So I can pull those out. Now, I'm going to rewrite the sum then with these pulled out. But I'm going to keep things on their sides just so we can see something here. So my rotational energy then could be written this way. 1/2, I pulled the 1/2 out over here, times this sum times omega squared. Now I've got the parentheses here so that you realize omega squared, it's not inside the summation now. Okay? And you'll see why I write it that way here in just a minute. So what I get is 1/2 times this thing, the summation of m sub I r sub I squared times omega squared. Now this piece right here is really special to rotational motion. This is what we call the moment of inertia. So the moment of inertia mathematically is every piece of this object, I take its mass, I multiply it by its distance from the axis of rotation squared, and then I add that up for all the little pieces. In other words, the moment of inertia is just m1 r1 squared plus m2 r2 squared plus m3 r3 squared, and so on until we get to the last little particle we divvied this dude up into. Okay? This is the moment of inertia, and it's really important in rotational motion. We're going to see why here in just a second. Now, if you look at the summation, though, I want to go ahead and bring some things out. The moment of inertia depends on some important features. One of those is the shape of the object. The shape of the object is going to determine how far away a piece can get from the axis of rotation. So the shape of the object matters. The way in which the mass is distributed throughout the shape is going to matter too. If I have a lot of mass that's out here and it's not maybe as dense towards the axis, that's going to give me a larger moment of inertia. We'll talk about that here in just a second. But the big thing I want you to see right now is that the moment of inertia ultimately depends on the location of that axis of rotation. Okay, my rotational axis is here right now, and that means that this object has a certain value for r, this object has another r, and this object has its r. But if I move that axis of rotation, say I put it right here, try to kind of center it up, that's going to change all my r values. And if all my r values change, then my moment of inertia will change. Okay? So, I know you're going, well, how will we use this? Well, we'll get to that in just a second. But I do want you to understand the moment of inertia varies for an object based on where that axis of rotation is located. Okay, and that's an important thing to keep in mind. Now, so if this is what we call the moment of inertia, then I could rewrite my energy equation. I'm going to drop the total now. Just rotational energy is given by this. Then it's 1/2 I omega squared. Okay? And so we can reduce it down to this simple little equation. And it turns out, I'm going to show you in a second, these I values have been tabulated for a lot of important shapes. And so that's something you would get out of the table. Okay? But what I want to pick up on right now is something very interesting. Look at the form of this equation. K is 1/2 I omega squared. Well, okay, that kind of looks like another equation. Let's pull these up. You remember the equation for linear, or for the kinetic energy of an object undergoing linear motion? The kinetic energy was 1/2 mv squared. Now the kinetic energy, or the energy of rotation, is 1/2 I omega squared. Look, we've got 1/2s in both of them. We've got velocities in both of them. For the linear energy, when an object's undergoing linear motion, we use the linear velocity, v squared. But for the rotational motion, we've got the angular velocity squared, but they're both velocities. Okay? And then so what we have here in the middle, we've got m for that's involved in the calculating the energy of an object moving in a line. We've got the moment of inertia. Okay? Now this brings out, these equations are so similar that we see that there's got to be a connection between the way m works, the mass works, for an object moving in a line, and the way I works for an object that's rotating. And here's the key point. You see, the moment of inertia is to rotational motion what mass is to linear motion. We refer to mass as the inertial mass. In other words, the mass of an object, it's determinative in how an object responds to a force that's trying to change its state of motion. Larger mass objects reduce changes in their state of motion better than smaller mass objects do. Well, the moment of inertia plays that role when it comes to rotation. Objects with larger moments of inertia, well, they resist changes in rotational motion a lot more effectively than those with smaller moments of inertia. And so, the moment of inertia is to rotational motion what mass is to linear motion. Okay? So it's really important. Everything that goes on rotationally depends in one way or another upon that moment of inertia for the object that you're looking at. Okay, so let me just demonstrate what I'm talking about here. Taking a picture out of your book. What we have here, the entirety of this object, this part and this part, is equal to the mass of it is equal to the mass of this whole thing, this part plus this edge. The only difference is that this guy has a lot more mass concentrated at the center, and this guy has more of its mass concentrated out at the edge. Now let's go back to our equation for the moments of inertia. You notice that the moment of inertia really depends on how far each little piece is from the axis of rotation. Now our axis of rotation for this is right through the center. Well, let's think about what this equation implies for these two situations. This guy, most of his mass is concentrated at the center. He's got more mass concentrated at the center. That means that it's closer to that axis of rotation. In other words, that mass that's at the center has really small R values, okay? So you're not going to get as big of a contribution to the moment of inertia. And so because that mass is concentrated towards the center, then it's going to have a smaller moment of inertia. But now here's this object. It's got the same overall amount of mass as this guy does, but its mass is more out towards the edge. Well, that mass that's concentrated at the rim, well, it's further from the axis of rotation, so it's going to have larger R values when you calculate its moment of inertia, and that means it's going to have a larger moment of inertia. Okay? So the distribution of the mass matters. Now what this means is this object, it's going to be a heck of a lot easier to start or stop it spinning than this object is, because this one's got a larger moment of inertia. It's going to be harder to stop this from spinning or start it spinning. So, and so you can already see that moment of inertia is going to determine how that object responds when we start exerting forces on it, trying to either make it speed up or slow down its rate of rotation. Okay? And so really then the key to being able to understand how a rotating object is going to respond to external forces is that we need to find its moment of inertia, I. Now, fortunately for a lot of basic shapes, which tend to be the shapes we work with in most cases, there's already been work done to find those moment of inertia. To actually do it for any object, you've got to go into some calculus and turn this into an integral. This becomes the integral of dm times r sub I squared. And that can get kind of complicated, and I don't know if you guys have done three-dimensional integrals yet. So I'm not really going to push that issue. But the nice thing is, for a lot of shapes, we already have the moments of inertia calculated. So let me just go over a few of these because they illustrate some things. Let's look on this side first. We've got a thin rod here, okay? And what we have is an axis that's going right through the middle of it, okay? It's going through the center of that rod. Well, it turns out that if you want to know the moment of inertia, you take 1/12 of the overall mass of the rod, that's what the big M means here, times the length of the rod squared, okay? So it's in a table. And anything we do, I'm going to be using basic shapes that we can, that have been tabulated. What I want to point out, though, is let's look at this thin rod down here. It's the same situation as we have up here, same mass, but now we're going to rotate it around an axis out here. See, this guy's spinning around this axis in the middle. Now this guy's going to spin around this axis that's at the end. Same mass as this one, same length as this one, but look at what the moment of inertia is now. It's 1/3 the overall mass times L squared. The ML squareds are the same, but we've got these different fractions out front. Here it's 1/12, here it's 1/3. But now that should, so it's different because the axis has changed. And I want you to notice this has changed in a way that we should expect, because this one is going to be larger. You take 1/12 of something, that's going to be smaller than 1/3 of that something, right? So this actually has a larger moment of inertia, but that makes sense. Because by moving the axis from here out to the end, what we've done is we've pushed more mass further away from the axis of rotation. So we got more mass that's now going to have larger distances from the axis, and so we get a larger moment of inertia, okay? So so that's how this table works. The solid sphere versus the spherical sphere, down here. Both of these spheres have the same overall shape, okay? Or sorry, the same mass, but they don't have the same shape. Now, both of them are rotating about the same axis. Let's look. So for a solid sphere, we got an axis going through the center, okay? And so it's going through a diameter. And so what we get then is that the moment of inertia for a solid sphere is 2/5 mr squared. But if we take another spherical shape, but this is just a shell now, it's hollow inside, but it's got the same mass as this, the same radius as this. Now, the moment of inertia is 2/3 mr squared. So same mr squareds, but this one's going to be larger. Well, that's because if it's got the same mass as this one does, that means this one has a lot more mass further away from the axis of rotation. And so we get a larger one. Now, what I want you to see here, this one illustrated that the location of the axis matters. This one illustrates that the distribution of the mass matters, right? Same axis, but if we have all the mass out at the edge, well, now we're going to get a larger moment of inertia. And so this is in your book. I took this out of your book, but it's pretty simple to use. Now, let's not forget about the energy thing. That's what got us here. But let's see how we can calculate the kinetic energy and put this table and the idea of the moment of inertia together with it all. So let's say we have a hollow metal sphere, and it's rotating about an axis that goes through its center with of an angular velocity of 2.5 radians per second. And so if the sphere has a mass of 12 kilograms and a radius of 75 centimeters, what is its rotational energy? Well, I'm just going to draw a picture here. No, it looks like a cue ball. I couldn't get a metallic looking sphere in PowerPoint. So, but this is our metal sphere right here. Maybe it's been painted white. All right. It's rotating about an axis that goes through its center. It's going at a rate of 2.4. We'll see if I made the mistake. Right now I'm saying 2.4 radians per second. I bet that's what I kept up with. So we'll say 2.4 radians per second, and it's got a radius of 75 centimeters. Now, if we want to calculate the energy of rotation, that's 1/2 I omega squared. Well, I went and looked in the table. Okay, what I have here in parentheses is that moment of inertia. This is I. So that's 1/2 times 2/3 mr squared omega squared. And so what I can do then is just substitute all my values in here. So the 2/6 right here, this comes from the 1/2 times the 2/3. Then my mass is 12 kilograms. My radius, now notice I had to change it to meters. It's 0.75 meters. And my angular velocity, oh, I did keep it with what I had in the problem. It's 2.5 radians per second. So this is the mistake right here. But, you know, at 20 minutes into this thing, I'm not going back and starting over. So this should have said 2.5. But I've substituted everything into my equation. And when I do that, I get that the rotational energy is 5.63 joules. So that's how you calculate the rotational energy of an object. This is the key equation. But this should be easy to remember. If you remember kinetic energy is 1/2 mv squared, then you can remember the kinetic energy of rotation. We're just going to take out m and substitute in I. We're going to take out v and substitute in omega. And that is how you calculate the energy of rotation.